Wouldn't that be easy to just not get them all done and win $10?
I have 2 of them right now.
How about if you don't get them done, you give me $10. If you do get them done, I'll get everybody lunch. I'm just gonna get everybody lunch anyway. But
So he's extorting us, kind of.
What lab are you on? I've got the first 2. We're about halfway through, so I guess.
I think he might win that.
What's the last day for this class?
May something.
That makes sense. I thought it was March something, and I was trying to figure out how that worked. And I thought that I was wrong.
Are you serious? Oh. Ouch. Yeah. I'm supposed to need to fill up. I was so last. It's gonna suck like
Do you remember when we did motor controls? Did I do that? Would have been last spring, right?
Industrial.
Yeah, or you might have had it in the summer, but we went through those learning activity packets, right, for some motor theory and synchronous motors and asynchronous, like all that squirrel cage, all that bullshit. Okay, so this is along. Yeah.
They were
Yep.
PDFs, yeah.
This is along the same kind of lines, but the reason this is thrown into this class because for things like robotics, and then we're going to talk about basic CNC type programming, so numerical control. The goal is just to get you familiar. You guys aren't going to be robot experts. I'm not a robot expert, but I could service one if I really wanted to take one apart and change a motor. So we go over things like motor theory, kind of briefly, and then next week we'll talk about, well, yeah, well, what is today, Wednesday? Let's plan on the quiz over this spiel a week from today, Wednesday. I still want to give you guys plenty of lab time. And then the following week we'll do CNC stuff. And we're coming up on break, aren't we?
Yeah.
Anybody know off the top of their head when that is?
It's like March 20 something. I thought it was the 20 something. 17th?
The week of the 14th.
I'm just not.
And then we come back on the 21st.
Oh. That's what I think.
So we get like 10 days off.
So it looks like the week after next. So we'll start into the CNC stuff the week after break, the week of the 21st. Okie dokie. But just keep in mind that a week from today, we'll take a little quiz on this spiel. So, okay. I'm going to skip through a lot of these slides because they're either I don't care or you probably already know them, but two basic types or classifications of motors are DC and AC. And then the AC motors we can classify as either single phase or polyphase. And could you tell the difference by looking at one, if one was single phase or three-phase motor? How could you tell? Usually has this capacitor, and in this picture, there's this little bump out here on the top of it. So if you take that little cover plate off, there's a capacitor underneath there. That's not always the case. Sometimes those are built into the casing of the motor too. But a lot of times you can tell the difference between them just by finding that thing. And then three-phase motors typically will handle a lot of the bigger load applications. And then what is the little thing on the side, the little junction box called? Where you make up the wiring? These little guys? Make up the wiring? It's a funny name. Close. It's a dick box. Yep, the dick box. It's the pecker head. But for the quiz, dick box. Actually, that's not on the quiz. But if I asked you, how are DC motors configured? Would you be able to list those four things?
Like right now, or? I was gonna say, when you have it up there.
If I said DC motors are going to be classified either permanent magnet, series wound, shunt wound, or something else. Got it? Cool. All right, and then here's more of a breakdown of AC motors. DC, so the top is DC, and it's the same thing you saw on the last slide, but this gets more in depth on the different types of single phase versus polyphase. In those learning activity packets that you guys did last spring, you saw things like squirrel cage, wound rotor, synchronous, induction. I don't really care to get too much into exactly what all those different things mean, because what we do in the field is a lot of troubleshooting. If we're not installing, we're troubleshooting, right? And we're taking things apart and trying to figure out, is it worth my time or my company's time to replace this or have it serviced? A lot of times that's just a matter of looking at the bearings or something else. But you should be able to take the casing off the back of the motor, look in there and see all those windings and understand how that thing operates. And you all know that, right? We've been through that enough. And three-phase, and how do you change the rotation of a three-phase motor? Any two of the leads, and you understand why, right? Because you're either hitting ABC or CBA in that rotating magnetic field. Okay, good. But with this slide, questions are so dumb. What would you say the yellow box, the universal motors, what makes them handy? You can use them either in what or what? AC or DC. right? And that's why it's stuck in between there. So handy, but expensive. And the two different separate classifications of AC motor, they're either going to be single or poly or single or three phase. Cool. Huh? I don't know why it says poly because I've never seen yeah. Because even if you're doing like say 240 and you got two hots, it's still single phase. So anybody know why that is? Okay, so three phases, you got three hots, right? In between, so 120, 208. Between any two of them, you've got 208 volts, right? And single phase, let's say 277 volt. You've got a hot and a neutral. And the difference of potential between them is 277 volts. So in your house, like your dryer or your stove, that might be, if it's electric, 240 volts, and then you got two hots there. So why is that still considered single phase? Right. So at the primary, wherever that's coming in, you know, Ameren brings three phase, just like you have in your house, out to a subdivision or to campus here, right? And then you've got a transformer that takes those tens of thousands of volts and knocks them down to usable voltage. But with single phase, so coming into your house, we've got 120, 240, that's only coming off of one of those phases coming from Ameren, right? And then depending on where that's tapped at the transformer, that's how you get either 120 to ground or 240 between them. Make sense? That confused me for the longest time. Like, this is fucking two phase. No, it's not. It's single phase, and that's why. Okay. So universal motor can be used with AC or DC, and then AC motors can be divided between two different classifications. What are they? Single and three phase. And we just talked about this a little bit, but voltage applied to the stator causes that rotating magnetic field. And it doesn't matter if it's AC or DC, it's going to create that or single phase or three phase, it's going to create that rotating magnetic field. All right, I'm just not going to use this question because it's stupid. Next. How many watts are in 1 horsepower? Oh, shit. Damn it. Did you know that before today? Because I should have told you that a long time ago. But that's a pretty common number you would need to know in the field. 746 watts, 1 horsepower. So get a 1 horse motor that would output the equivalent power of 7 100 watt light bulbs and 150 watt light bulb. Make sense? Horsepower is a measure of how fast work is being done. And another way to say that would be the amount of work being done over a given amount of time. Work is the force times distance. So the work it takes to perform a task is measured in the terms of the force exerted to move something a certain distance. Whereas horsepower, so you would kind of think that horsepower would be work. It's not. It's the amount of work being done in a given time. So there's 3 variables actually in horsepower, because work is force times distance. So if I push this little remote, which weighs 1 pound, 1 foot, huh? Just a second now. And it's exciting. This is really exciting, but if this is a pound worth of, is this a pound of weight and I push it a foot, that's 1 foot-pound, right? But that has nothing to do with power because horsepower depends on how long it took me to do that, right? So if horsepower is the amount of work being done over a given amount of time, if I was to push this 1 pound weight 1 foot and it took one second, what would that look like? Foot-pound per second. So foot times pound divided by 1 second. Correct. So, in other words, in 1 minute, this is important. In 1 minute, 1 horsepower will do 33,000 foot-pounds of torque. So torque is a rotational force. That's what a motor is doing in 1 minute. So 33,000 foot-pounds per minute is what 1 horsepower is equal to. Let me back up. 1 horsepower is equal to how many foot-pounds of work in 1 minute? 33,000. And I'm sure that if we did a bunch of nonsense examples of that, you would be able to convert foot-pounds per minute into horsepower, right? If I gave you inch-pounds per second, you could convert that to horsepower. Not that you would need to for the quiz, because you don't, by the way, but cool. This is why I skipped through this stuff, because in the field, are we ever going to get, hey, Will, how many horsepower do we need for this inch-pounds per second?
5.
Yes, you're never going to need to know that. But why would you need to be able to know what size motor you need? Or give me an example of.
Because you need to have a certain amount of things to be able to turn on and work. So you have to
Right.
know what you need done so that you can size the motor
Right. Depending on where you guys end up. And I'm trying to just, okay, real life. Dryer. Dryer has a motor in it. And somewhere in the specifications of that, it's going to tell you what kind of torque. That's a bad example. It's a really bad example. Okay. Real life. Your dryer is fucked. It's smoked. You can see it. It's black. It ain't spinning. You turn it on and it hums and it stinks. So what do you replace it with? A new dryer, maybe.
A new motor.
A new motor. And how do you size it? Right. But I have seen times in the past where we actually didn't have to figure out what size motor to use. One that off the top of my head was in a lift station, right? So a lift station is like an underground pit that basically pumps water to a higher elevation, whether it's sanitary or storm or whatever. There's places where water isn't high enough in elevation for it to drain properly, so they put in lift stations and it will pump it up to where it can drain properly, right? And water is heavy, and we've had to calculate depending on the volume of the lift station and how high up we would allow those motors or to start running versus when they'd have to finish running. And they were big motors because this was like a 40-year-old lift station and you couldn't read the nameplate on the motors. They're just a big fucking motor. Well, you can't call Baldor and say, hey, I need a big fucking motor. You know, you have to be able to have some kind of, last thing you want to do is put a tens of thousands of dollars worth of motors and pumps in somewhere and then have it fail in a week because you undersized it, right? So, all right, off my spiel. So I just mentioned this, but what is rotational force? Torque. That's an important one. Rotational force, but you might see a question that says twisting force, which is stupid. All right, we'll come back to one of these examples. I want to get through. I don't care. I don't care. Okay. Load, torque, and speed. You guys saw this in troubleshooting, but what happens when you're missing one phase of a three-phase motor? You guys would troubleshoot this out there on those trainers. You get kind of this humming sound, right? And the motor's bogged down when I would tighten that pulley up on the shaft. What is happening in that motor? What causes it to overheat? Electrically. Right, you're missing some of that force. But if you're missing a phase, as you're increasing the load on the shaft, there's something is increasing exponentially that makes the motor itself heat up electrically. The current, right? So if I was to increase the torque on the motor, would the current go up or down? The current would, yes. And torque is what? Rotational force, twisting force. So if I don't mess with if I didn't put a fault in there, did not have a missing phase, and it was still running how it was supposed to at the speed it was supposed to on those. As I increase that load, there's two things that increase as well. And we just talked about both of them. So you increase the load on a motor, the goes, and the, right. Let me say that again. Increase the load on the motor, two things go up. Torque and the current. Very good. It's common sense stuff, but it just helps to spell it out, especially when you know you're going to see it on a quiz. Oh, I'm such an idiot. What about when you start a motor? Not with a drive, with a motor starter. You just hit it with 208 volts. What happens to the current? Yep, there's something called an inrush of current. And all it is that in the same sense that when the shaft is bogged down and the motor's going, that current is really high. On a motor, it doesn't have that initial startup. So as it's starting to rev up, that very first amount of time, very split second, that inrush of current goes very high. And what you need to know is that the startup torque for a motor is actually more than full load torque. So what does full load torque mean?
The torque when it's running at its speed.
Yes, yes. But on the nameplate, you're going to see this value on the motor nameplate, and that's the rated amount of torque you're allowed to put on it per the manufacturer, right? So if you go above that torque, the current's going to be too high and you could damage the windings, right? But for a split second, when you start up that motor, that inrush current is actually more than full load torque. Yeah, full load is different than locked rotor. This all gives kind of an explanation of everything we just talked about. I'm sure you guys will all study this very hard. Oh, there's your locked. And a locked rotor conditions stall and startup. So yes, startup current, I guess, would be, so I don't know if you can classify it as the same thing. But the motor is not doing work, so the horsepower delivered is also zero. No work is being done. I think that's the last thing that I wanted you to know for the quiz. And a couple more things. So these are actually not even in the PowerPoint, but we can kind of use for the first one, a little bit of common sense. But if a motor was 100% efficient, is every motor on the planet efficient 100%? Is it even possible? Why? Exactly right. Some of the power consumption done by the motor is lost in the form of heat or eddy currents. But theoretically, if it was 100% efficient, it would produce 1 horsepower for every how many watts consumed? 746. Man, you guys are good. I'm so proud of you. All right, this one is not anywhere in this PowerPoint, but motor manufacturers are required to produce motors that have an efficiency rating of at least how many percent? What would you guess? What?
80. Am I right?
Yeah. Is it just a random guess?
No, it was an educated guess.
Yeah, I'm sure.
It was.
Where'd you hear that?
From residential wiring.
Really?
Yeah.
It's amazing. Yes, manufacturers are required to produce at least 80% efficient motors. Okay. So this is a graph of speed versus the motor efficiency. And you would kind of think that as the motor is speeding up with lower torque on it, or lower load, it would be more efficient than if you put higher load on it, right? But this one confused me always too. In reality, the way that they're designed, they're designed to run at a certain amount of torque, and they're actually most efficient if you run them at or near full load. Does that make sense?
Going faster doesn't make it work.
No, a motor is going to spin as fast as it's going to spin unless you have it on drive. And that's because of hertz, right? We're given a certain amount of hertz at the, so depending on how big the rotor and the stator are, you've got a circumference there. It's going to spin a certain amount of times per second, and however far apart that diameter is, there was a slide, but I think it's somewhere between, you could look at any motor out there and it's going to be somewhere close to 3,500 revolutions per minute. That's normal. But if the speed is constantly, I see how, be careful, I don't want to word this. If we did have it on a drive and we were running it at half speed at a certain amount of torque, it's going to be less efficient than if we were running it at full speed at full load torque. Does that make sense? So maximum, and you can tell by looking at this graph that full load speed and near or at full load speed is where it is most efficient. This one gets up to like, I don't know, 85 or 90% efficiency. But at or near full load is where a motor is most efficient. Yes.
So right where it locks straight down to zero again, after
Mm-hmm.
there's nothing on it. Why is that? Like I get it because you need weight on it. But what causes?
The efficiency is what's going down, not the speed. Right?
Like I get with the torque, you know, need something that's on the motor.
That's like, that's what we're running faster than it's supposed to be.
Oh.
The efficiency is going down.
Yeah, this is
going
not
down.
saying anything about torque.
That's efficiency.
This is just saying, and this graph, the hump on the graph could be anywhere on here, right? They just,
Whatever the full load speed is.
right.
Because the efficiency is decreases when you go above.
Why is it going down?
Because if you run it past the full load speed rated for the motor, that's going to start to lose efficiency quickly.
Oh.
So remember in your labs when you did the VFD laps, learning activity packets, and it actually let you run it past 60 hertz. I don't remember what that amount was, but you can run a motor faster than 60 hertz. It's just, you start to quickly lose efficiency. So it's not necessarily saying that the motor will burn up or stall, but eventually it will. It's only designed to speed at a certain rate. So full load speed is what it's saying, is where you get your maximum efficiency. Okay. Did that answer your question? Yeah.
Like a ceiling fan in a house.
Uh-huh.
Like usually at 3 different speeds.
Uh-huh.
Whatever the full load speed is actually full release time.
Yeah.
Some people say like
Oh.
you're always
Good call.
Yes. The only thing that I question on that is that if that's a single phase motor, it might have different, you might be switching a certain number of sets of windings on and off too. You know what I
can
mean?
just say that to someone and it'll sound smart.
It's an interesting question, but yeah.
I feel like I've heard before, like having a high is not actually full. I thought that was why.
It would depend on.
Yeah, it's a really good question. Because you'd think that a fan is really not, there's not much load there. I mean, once it gets up to speed. But yeah, I mean, according to this, I would think that it's, Yeah. Or, and so what I'm thinking then is, well, let's do it and put an amp probe on it. But I wonder if even the current draw wouldn't show that. Like the efficiency could be that at speed number 2, your current draw is the same or even less, but you have more heat dissipated out of the windings at speed number 2 because it's not as efficient. But it's a good question.
Might be-
Should put that on Mythbusters. Is that show even still on?
Yeah, it is, but you have to go up.
Oh yeah. Okay. Will already answered this question. Losses in a motor show up in the form of heat. Yeah, it's just a really shitty picture.
Oh, is
It's a
it
nice
really?
picture though, really nice picture. Electrical power.
I don't have my glasses, so it looks, everything looks like probably not that.
When do you think a motor would overheat the quickest? When it is at full load speed on startup, producing its rated power, or when it's stalled?
Stalled.
Very good. And that is C, stall speed, right? Shaw. Imagine how long it would take if we went through every slide on this thing. Last one. These are pretty common sense guidelines, but nobody ever lubricates, cleans, replaces the contacts on a motor unless they're big, expensive motors. Anything to reduce friction in the motor will help. Well, that's another thing that once it's there and installed, you're really not going to mess with it unless it burns up. Unless you're doing preventative maintenance on a huge, expensive motor, that doesn't come into play. But the most common and kind of the obvious answer to a question of what is the most common cause of a motor burning up, overloading it for long periods of time. Cool. That covers everything that I wanted to go over with you. And I think we'll even skip the math example because it's really not applicable. So that is it. Everybody good? Any questions on any of that? All right, we'll plan on a quiz a week from today on that. You guys can work on whatever you want to work on now.